So this problem is asked, so we have a membrane on current of a neuron to a voltage clamp step shown below, and okay. So this is a voltage clamp, so we are controlling the voltage and then we are measuring the current, right? So that's why we have this step function looking thing with the voltage, which is what we're controlling, and we're measuring this current. And they made this like IV curve, or so not really exactly IV curve, because for this plot, what we're showing here is the voltage on the axis, membrane voltage on the x-axis, and then on the y-axis we have the probability of the specific channel opening, where one is like 100% times open, and then 0.5 is like 50%. Oh, okay. So the question is asking whether this specific neuron is activated by depolarization or hyperpolarization. And how we can tell is from this plot is that as the voltage, the membrane voltage goes up to -60 to -80, whereas it reaches, the probability of channel opening becomes 1. So it's getting activated, right? So because it's getting activated at the lower membrane voltage of -80 to -60, we can tell it's a hyperpolarization activation channel. And as we all know, the hyperpolarization, let me draw this out real quick. We have this time versus voltage curve, and then we have some sort of, kind of looks like that. Well, and then this is the resting membrane voltage. And when one that goes below the resting membrane voltage, we call it hyperpolarization. And this is usually like negative 60-ish, 60 to 80, but any millivolt. Anyway, so that's what it is. And how do we know whether this is an inward current or like outward current, right? So just as a convention for in electrophysiology, the ion that's like coming in to the cell is a negative, as you can see here, inward current, and then outward current is a positive, right? So going back, we see that as we goes to as the current is going down, and when it goes to resting membrane voltage, and it's going inward, so it's an inward current. And it's second question asking what is the approximate value of the time constant, and it's, as we all know, it's just like one time constant is like 63% of the steady state value, and for current, we know that so steady state is 3, and we may think, oh, then maybe the value of the -2 is about 63% of the -3, and we should just a time when, oh, well, like here, and then maybe 0.05 seconds could be my time constant. However, this instant drop is called leakage current, and I'll explain that later, but it is not of this the neuron of our interest, but it is of some other like variables. So we kind of ignore that, and we just look at this magnitude from -1 to -3, which is 2, and then 63% of the 2 is like maybe about like here. So at that point, it's around 0.1 second, and time constant we know is about 0.1 second. And what is the amplitude of leakage current when the membrane voltage step from -20 millivolt to -60 millivolt? As I mentioned, this instantaneous change in current as the voltage change is called leakage current, because the current, the ion channel of our interest has to follow this curve. And it's a probability function. It's not going from 0 to 1. And they follow this exponential function, like a instead of instantaneous change. So we know it's not. This is a side effect of the leakage current, not the effect of the neuron of our. The ion channel of our interest. So the amplitude of leakage current, when it goes from -20 to -60, we see that it's just about 1, magnitude of 1 and negative 1. So yeah, -1 nanoamp. And the amplitude of the fully activated this current. So leakage current is the instantaneous change, and the fully activated amplitude is the remaining, the exponential change. So that we know is like -3 minus -1, so we got 2. And if it were to be from -20, what is the steady state value of the current? So when the membrane is stepped from -20 to -40, so instead of -60, if it were to be -40, like what would be the steady state like value of this current over here? And we can infer it from here that if we were to go from so we see that -20 to -60 is like from 0 to like 1, so of the probability of like channel opening. So we know that the corresponding value of the current at each end, so at here is 0 nanoamp, at 1 it is -3. So at -40, from -40 we could suspect it's like the half of the steady state value, which is -3. And one may say, well then isn't it -1.5 because it's like the half of -3 nanoamp. But what we need to be careful about is that this is the leakage current, and that's kind of like just always happen regardless of what we do. So what we should pay attention to, and what we can control, is here, the fully activated amplitude. So this previously from -20 to -60 is like 2, but now that it's going to be halved, so it's going to be from -2 to it's going to become -1 at this value at 0.5. And we add the -1 and then leakage current, which is also -1, then we'll get -2. And then this is 2, this is like the cell membrane of the nerves. And the scientists show that protein label 1 has a voltage gate as well as an inactivation gate, while protein 2 and 3 lack this dual gate architecture. Which ion is most likely to be controlled by protein 1? And we all know that the sodium is the only one that has the inactivation gate, because sodium is a positive feedback cycle. So once it, you know how it this is time voltage curve, it goes like shoo, and then goes down. And then comes back up, and the one that make it go up is controlled by sodium, and it has a positive feedback loop. And if it didn't have the inactivation gate, it would just continue to go up, and it won't lead to the best result for cells because it's going to rupture or something. So it needs this like inactivation gate to stop its positive feedback cycle. So the answer is sodium. This protein 2 is responsible for repolarization following the peak of an action potential. And we know that, so the one that drives it down is potassium. So this is going to be potassium. And then 3, active transport pump, restores the normal balance of sodium and potassium every time when action potential travels through the regions of action. So the ratio is 3 sodium out of the cell and 2 potassium into the cell. You just got to memorize it. So the refractory period, which channel contributed most to the absolute refractory period, and So when the reason why it can't fire is because the sodium channel is inactivated by its inhibitory protein, as we kind of talked about in the first question, the inactivation gate. So because of that, it is the sodium ion, which is the protein 1. I'm going to move on from here. Then let's go with this. Estimate the value of the time constant and the steady state current at each voltage. So here we are, for time constant, it's always the time constant is like the time at which the current, the value reaches the 63% of the steady state value. Time in which the value reaches 63% of the steady state value. So here we see 0.6 is like the steady state value. So 63%, which is about 2/3, is like 0.4, right? And 0.4 is like it's like maybe 1.5 millisecond, maybe 1 millisecond, something like that, right? So that's the time, that's the joule, and the steady state current would be 0.6 milliamp per square centimeter for a control voltage of -20. And then we can do the same thing for like the rest of it, remaining one. For -40, in that case, 0.4 is the steady state current, and then so 63% value would be something somewhere here, and we can be like 2.5 milliseconds, and so on and so forth. Now, what is the value of the EY, which is the equilibrium potential? So equilibrium potential is really, in other words, different way to say steady state value of this current. So, or steady state equilibrium potential is like a membrane voltage that is like energetically stable, or like the lowest. And because it's steady state, the current has to be 0, because current is the number of ions that's kind of passing through, or the amount of ions that's passing through the membrane. And steady state, which means it's happening in the infinite times. And if there's like even a single ion that's like going out of the cell for infinite amount of time, cell will run out of ions, right? So it doesn't make sense. So at steady state, or at the equilibrium potential, the number of ions has to be 0. And because of that, the equilibrium potential is -80 millivolt. And remaining C will be done on paper.